Okay, so if you recall here, we went over kind of a set of steps that you should take whenever solving, okay, a work energy theorem question. We said obviously first you write down your givens, and then from your givens, really the most important step is to figure out what kind of energy is changing in that question. Is it kinetic energy or is it potential energy? The work part isn't going to change. That's still going to be either W or FD, okay, which is still W. But what is going to change is, are you setting that equal to m times g times h, or are you setting it equal to 1/2 mv squared? All right, and that's what you have to decide. Is speed changing? Then kinetic energy is changing. If height is changing, then potential energy is changing. All right, and that's kind of the big decision for each one. Now, this one's asking how high does the box get? So what kind of energy is changing in number 1? Potential, because the height is changing. Okay. Now, in number 2, we've got it's kicked from rest to 21 meters per second. That's kinetic energy because the speed's changing. All right. So we have to identify those kind of first off. All right. So for our first one here, okay, give them a mark for work equals a change in potential energy. All right. I'm not giving a mark for givens here for some reason. I'm not sure why, but okay. Work equals delta EP on this one. Okay. So give them a mark for recognizing that. Okay. And then, since it was at ground level at the beginning, what's the initial potential energy? 0. All right? So that's why I can just write m times g times h. Theoretically, what I should write is this: m times g times hf minus m times g times hi. But since this is 0 anyway, there's not really any point. Right? I can just write m times g times h. All right? Plug in my numbers. So here's their second mark. Okay, 8.5 kilograms times 9.81 times 1.6 meters, okay, gives us 133.416 joules of work. Okay. Questions on that one? Okay, for number 2, sorry, no, 2 slides. Oh, whoops. Sorry. Sorry, guys. Stop. We'll just do this again here. Okay. So we're still going to have work is delta EP. That's still going to be your first mark. Sorry, guys. What happened on that one? Okay. Work is still delta EP. 1 mark. All right. Our next one here is that we have to manipulate to find out how high the box gets. Okay. So we're taking m times g times h equals 183 joules. So divide both sides by m times g. Okay, and we're left with h. Give them a mark if they did that, or if they went straight to numbers, 183 over 8.5 times 9.81. Maybe they did that. Okay, so 1 mark for that step there. Okay, and then 183 divided by 8.5 times 9.81. All right, gives us 2.19 meters. Okay. Sorry, I forgot I had changed that question. Any other questions on the first one? Let's make sure the second one matches. Yes. Okay. All right. So we've got givens here, and I'm pretty sure I gave a mark for those. I got the marks all different here too. Okay. Let's just fix this. Give them a mark for givens on number 1 because I'm saying number 1 is out of 4. Give them a mark for givens on number 2 as well, because I always do that. I don't know why I would have gone away from that. So, okay, first one's out of 4 then. Just give them an extra mark. Okay, number 2, we'll start out with a mark for this. Okay, mass was 0.75, V was 21 meters per second. Okay, we should probably say VF and VI here. This would have been 0. All right, work is the change in energy, which means final kinetic minus initial kinetic. But since this thing started from rest, what was our initial kinetic? 0. All right, so we don't really need to write that. And again, it just ends up being that the work is 1/2 mv squared, right? Using the only velocity, or speed, sorry, that we were given. All right, so mark for this step. Okay, mark for plugging in the numbers, 1/2 times 0.75 times 21 squared, and then mark for the final answer, 165.3755 joules. Okay, so that one's out of 4 as well, we'll say. Okay, questions on number 2? All right, these are easier than the ones that are on the worksheet. So if you struggled with these ones, I can only assume we haven't got very far onto the worksheet yet. All right? Especially considering this was going to be Tuesday's quiz. All right, so today we're working on that worksheet. And we're going to go over any ones that give you trouble. So if there's one you can't get, be sure to ask. All right? We got to know how to do this stuff. All right, give them a mark out of 8. Let them see it. Put it in the box, please. Work it. Okay, that's how you calculate work. You calculate work by going force times distance, but that's not what work is. What is work? Work is a transfer or change in energy. So, in this question it says 32 newtons of force is required to lift a box 3 meters vertically against the force of gravity. So, I have been given a force, okay, and that is 32 newtons. And I'm told a distance or a height, doesn't really matter. They're both the same in this case, okay? And that distance is 3.0 meters. First says, calculate the work done against gravity. Well, work is force times distance, and I have those two things. That's great, that's easy. Force times distance, 32 times 3 is 96 joules. All right? Then it says, calculate the potential energy of the box. And people are now looking at me and going, Coder, you didn't give me the mass of the box. I can't calculate this number. Yes, you can. The trick is that you already did. Because work is a change in energy. How much potential energy did the box have when it was sitting on the ground? 0. If you did 96 joules worth of work, you transferred 96 joules of energy to the box. How much energy does the box have now? 96 joules. Here's the situation, guys. You started here. You did. Okay, and here you had 0 joules of potential energy. You did 96 joules worth of work. That means that at this position there are 96 joules of of potential energy. Now, were I to drop the box that I had just lifted from this height down to the ground, how much kinetic energy would it have when it hit the ground? It would have 96 joules of kinetic energy when it hits the ground. Why? Because its potential energy will get converted to kinetic. It's going to speed up as it falls, will it not? And as it falls, its potential energy will decrease because its height will decrease. Well, that potential energy has to go somewhere. It turns into kinetic. Were my foot to be located right here, how much work would get done on my foot? 96 joules worth of energy. Okay, worth of work, sorry, would be done. You guys seeing the pattern here? Okay, work is a change in energy. That is the thing we have to remember. This is an application of that. It tests your understanding of it. Okay, if you understood that work was a change in energy, you knew right away how to do B. Okay, now you all know how to do B. Okay, work is a change in energy. That's going to come up like 3-4 times at least on that sheet. Right, where you have to say, oh, right, if I did that much work, that's the change in energy. That's how much energy it has now. Alex. Okay. An object gains 155 joules. If you gain 155 joules, is that a change in energy? What's the change in energy? Okay, no, we just covered that. Something is a change in energy. Work. If you gain 155 joules of energy, there's only one way for that to happen for you, and that is that much work has been done. There's 155 joules worth of work being done in this question. Okay? Work is force times distance. How far did it lift the box? Or the object, in this case? 1.2 meters. Is that D? Sure it is. Does that leave me with force? Okay, that's what the question was asking for, right? Is the force. Again, the math of this is not difficult. The thing you have to remember here is that work is a change in energy. You're going to get tired of me saying that. I hope you do. Because if you get tired of me saying that, it means that you know it already. Okay, work is a change in energy. Anytime you see gains this much energy, does this much work, that's W. All right? Or even if it loses this much energy, it's still a change. It doesn't matter whether it's gained or lost. Any change in energy is work. Either the work is being done or the work is being received. Okay? Either way, it's still a change. It's still work. All right? Any other ones? All right, keep going then. All right, so on number 6 here, okay, we have a rubber band that has a mass of 0.02 kilograms, okay, and all 320 joules of energy is kinetic. Okay, so we've got mass here, we've got EK is 320 joules. How fast is the rubber band going? So we're looking for V. Well, if I've got EK and V, I'm looking for V, this isn't a work question, it's just an energy question. Right? I know all but one of those. I don't know the speed. So I manipulate for V. So I divide both sides by half of M and square root to get V. Right? Most people forget the square root part. Right? And so we've got 320 over 0.5 times the mass, which was 0.02. Okay? And when we square root that, we should get a ridiculous speed, but a speed nonetheless. Okay, things going about half the speed of sound. You probably wouldn't want to stand in front of that rubber band. Okay. All right, another one. About 340 meters per second. It's fast. Okay, any others? All right, keep going then, guys. Okay, remember that a joule is a kilogram meter squared per second squared. What do your units for distance need to be in? Meters. In number 5, I give you the distance in centimeters, just trying to see if you're really paying attention. All right? Remember that if you want to get the right units for work, you've got to have the right units for distance and force. Okay? And in this case, if you go and multiply by 10, you're not going to get the right answer. All right, everybody follow me there? 10 centimeters has got to be converted to meters. That's 0.1 meters. Okay. Reason I want to look at number 7 is this is the most classic example of a work energy theorem question. I've had a bow and arrow or slingshot or catapult question on every unit exam I have ever written. All right? Because it's showing that the work I do becomes the energy of something else. Okay? When I do work on something, it turns into a form of energy. That energy can do work on something else, and that thing will now have energy. And this is a prime example. Okay? If I have a bow and arrow, okay, and I exert a force on it, I can calculate how much work I do as long as I know how far back I pull the arrow. And I do. I know both in this case. Okay? So I start out with this. It's asking me how fast the arrow is going to leave the bow. Well, when I draw back the bow, what's the speed of the arrow? 0. I'm just holding it there. It isn't moving. It has no kinetic energy at that point. But when it does leave the bow, it is moving. And it does have kinetic energy then. So the work done here will be equal to the change in kinetic energy of the arrow. All right? I do work. I pull back the bow. When I let the bow go, the bowstring does work on the arrow. Okay? And it can only do as much work on the arrow as I did in pulling back the bow. Everyone follow? It's a law of conservation of energy thing. Once I put energy into a system, that system has that much energy. Okay? And this system is the bow-arrow system. All right. Work is force times distance, and it is a change in kinetic energy. So that's going to be 1/2 mvf squared minus 1/2 mvi squared. But since we've already said that when it's sitting in the bow, it doesn't have any initial velocity, it also doesn't have any initial kinetic energy. So now I'm set up. All I have to do is find V. I know what the mass of the arrow is, and I know these two numbers here. All right, so force times distance over 1/2 of m square rooted will give me V. Everybody follow there? All right, now, what if I turned this question and I did it so that I was pointing the arrow straight up in the air? Could I ask you how high the arrow will go? Yes, and the only thing that will change is that this will change from 1/2 mv squared to what? m times g times h, because now I'm talking about a change in potential energy. All right? Sometimes I ask the question that way. All right? So when we plug in our numbers here, okay, we have 100 times 0.29 over 1/2 times 0.120, all square rooted. When we do that, we should get 22 meters per second. Okay? Guys, those are important ones to know how to do. Okay? That was very much like the quiz questions you had today. All right? And that's the kind of question I'm going to ask on the unit exam. Right? Not any harder than that. Okay.